Hello, and welcome back to another video with It's Dr. Dan, and today we're going to be learning about solution stoichiometry. Specifically, we're going to look about how to find molarity, volume, and mass. So when exactly do you have to use this? So solution stoichiometry is all about aqueous solutions, and when you are trying to mix them together to try to solve for volumes, masses, using molarity to try to do different stoichiometric conversions using a balanced chemical equation. These can tend to be the hardest stoichiometric equations to do just because it has to use that concept of molarity, which as we know is moles over liters, and can be very, very challenging to try to really master. So we're going to go through the steps and tips and tricks of how to solve these, going through different examples of problems that you may see in your introductory chemistry course to be able to try to help you solve them in your course. All right, so let's go take a look at the different steps. So when we're doing these reactions, the first thing that we need to do is when it comes to the steps is balancing the chemical equation. So sometimes this may involve predicting the chemical equation. The good news is that most solution equations typically are double replacement reactions. So you're going to be doing that inside-outside bonding together, and balancing them usually is some of the easier types of ones to balance, especially when you compare them to combustion, which tend to be really difficult. Now, after that, you always want to, after you check if it's balanced, if you generally see coefficients, that means it's already done for you. Then you want to write down your mole ratios that are important for your problem and all the given information that you have. This may include volumes, molarities, masses, and it's really important to try to stay organized while doing it. I'll go through exactly how I usually go through these problems so that you can stay organized too. Being organized is crucial because it's very easy to accidentally mix terms up. So read the word problems carefully and make sure you sort things out as you go. The last step is always let your units guide you. It's always generally helpful to have like a molar map to help guide the way that you're going to be canceling out units. So I'll be showing you exactly the process that I use to actually cancel these units out. Remember, opposites cancel when we're showing these. So let those units guide you to get you to that final answer. All right, let's look at our first example. The first problem is acid-base neutralization, which is a type of double replacement reaction, meaning that you have an acid, which is always led with an H in front of the name, reacting with a base that has a hydroxide ion at the end of the name. So this one's all about finding the volume. So what it's asking is how many liters of 0.1 molar HCl can be neutralized with 0.10 grams of magnesium hydroxide. So one thing to kind of point out is some key words here. One is the word neutralized. If you see that word, that's telling you that the reaction is going to completion. And that is essentially just letting you know, hey, that this is reacting. These are the two things that are going to be reacting together. So what we have here is we have HCl, which is the first part that we see, and it says that it's reacting with magnesium hydroxide. So the very first step that we have to do is we need to balance and predict the chemical equation. Now, as I kind of mentioned before, these are mainly all double replacement reactions. So how can you kind of quickly identify them? Well, you whip out essentially your different types of chemical recipes where we assign ions with letters. So hydrogen is an A, chlorine's a B, and then we add that to magnesium, which is C, and then the hydroxide OH ion is D. So we see A plus C, D. So now the way these always bond together is inside out. So the inside bond together and the outside bond together. So our first part is going to be pretty much H and OH are going to be bonding together. So making H2O. So H and then OH, we'll write that down. This will make it a little bit easier to balance as by kind of representing that. But keep in mind when you have HOH, that's just water in disguise. It's H2O. Then the inside bond together, which is magnesium chloride. Now, when we are trying to balance these different pieces, what one trick is using the polyatomics to balance. So meaning that if you look on the right-hand side of this equation, we see a hydroxide. There's two of them. So that means that you need two hydroxides on the right-hand side over here to match. Now, this is why I write H2O as HOH, because it helps illustrate the OH ion here. It makes it a little bit easier to see. So being that we have two OHs on the left, we also need to have two OHs on the right. So let's do that. We'll add a 2 here. So now that we are doing that, what we're now going to do is look at the different ions that are here as well. So being that we just did OH, we're going to kind of zigzag it to its partner and look at the hydrogens. Being that we separated these two, we have 2 hydrogens and we only have 1 on the left-hand side. So I'm going to add a 2 over here to balance out the hydrogens. Then as we can see, we'll zigzag over to chlorine. We see that we have 2 of them now. How many do we have on the right-hand side? We can see we have 2 over there. So everything is now balanced and happy. This is a balanced chemical equation. All right. Now, our next step of what we're going to be doing is we need to write down the given information and include all mole ratios that are important in the problem. So when we do that, what we got to do is read carefully what we have. We see that we have 0.10 moles of HCl. So with that, what we're going to do is write that down. And the thing that's really always important is trying to make sure we write everything down underneath of the different parts of our chemical equation. Then what we are going to do now is we are going to recopy all of the pieces of information that are really important. The first part was 0.1 molar HCl. We're going to write that under HCl so that way it stays with it. Now, the next part of information that was really important was how many grams of magnesium hydroxide we have, right? As we can see that we had 0.10 grams. So we're going to write that underneath of our magnesium hydroxide. And what it's asking is how much volume of HCl you have. So what we'll do is we'll put a V is equal to a question mark right underneath that, and that will help guide our thinking. Now, from there, what we'll now do is we need to try to let the units guide your thinking and thinking, okay, well, where do I start? Do I start with the molarity, which is a conversion factor, right? You have to remember that molarity, M, is moles over liters, right? Meaning you can flip it one way or another. How do you decide which way it goes? Versus grams is a term by itself. So there's no possible way for you to flip that fractionally when it comes to this math here. Because if you do flip it, it's going to lead to the units being in the denominator, and it's not going to make a lot of sense. So what we're going to start with then first is our mass. And well, what can we always convert these to? Well, if you kind of can remember, what is your goal in terms of conversions? It's always the mole. Can you convert mass to moles? And one way that you can always do that is, well, let's use molar mass. So what we're going to do is take 0.10 grams of magnesium hydroxide and convert that to moles using our molar mass. So what we'll do is we'll look up our value from our periodic table, and this is going to allow us to calculate what that is. So you'll take 1 magnesium, add it into 2 hydroxides, and you'll get about 58.306 grams for every 1 mole of hydroxide or of MgOH. All right, so now that we have that, what's the most important part of that is now that we see that our units are going to cancel. Grams is going to cancel grams, and now we have it in moles. But the thing is that we really want is we want to figure out what the volume is of HCl. So how do we go to that next step? Well, we have to convert it to moles of HCl. So what we're now going to do is we're going to take this conversion, kind of bring it down. We'll make it a little smaller for ourselves if it wants to cooperate. And how can we convert this to moles of HCl? Well, this is where that chemical equation is really important. As we can see here by reading it, we have 1 mole of magnesium hydroxide to every 2 moles of HCl. So what we're going to do is do that 1:2 ratio. We're going to use the chemical equation. So 1 mole of MgOH 2 is equivalent to 2 moles of HCl. Now, what that's going to give us is how many moles of HCl are in this particular reaction, which is one of the most important parts. Now, are we done? Well, we want liters. So how do we get to liters from here? Well, in order to get to the volume, which is the last step, we can use the molarity, right? So what we can essentially do is take that answer from the top here, and we are going to essentially multiply that by, or sorry, divide that by the molarity to cancel out our numbers. From earlier, we had 0.10 molarity. Well, what we're going to be doing is taking 0.10 moles over 1 liter, because that's equivalent to molarity, right? 0.10 big M is the same thing as saying 0.10 moles all over 1 liter. They're equivalent. So as a result, what we can do is trying to follow our numbers is that we can see moles canceled moles, and then our moles of HCl canceled moles of HCl. Okay, so that all cancels, leaving us with only liters. So just to kind of clean up the math here, how would this all work in your calculator? We would take 0.1, times it by 1, times by 2 moles, then times by 1 liter, and then we would divide it by what's on bottom, which is 58.306, it equals, and then divide it by 0.1. So what we would get for our final answer in the end is going to be 0.0343 liters, which we can then convert to milliliters, right? So essentially multiply that number by 1,000, and we would get 34.3 milliliters. So that would be how much volume it takes to neutralize, which is about how much it makes sense, right? Because something that's being able to be done in the lab, something you can measure. So as you can see with these problems, they're a little bit more involved. They take a little bit more time, but it's something that you can guide your way through your units canceling. Let's take a look at another example. Even though gasoline in the US no longer contains lead, this metal still persists in the environment as a toxin. Despite its toxicity, many paint pigments still contain lead. What volume of 1.50 molar lead to acetate contains 0.400 moles of lead 2 plus ion? Well, a lot of times when we're dealing with solutions, we have to actually understand dissociation equations. So with this particular one, we have lead 2 acetate, which means that you have lead 2 plus, right? That Roman numeral 2 means 2 plus, not the subscript. And we have that with the acetate anion, which is C2H3O2 minus. Now with this, we got to swap drop. So what we'll do is we'll put parentheses around our ion and bring the 2 down outside of the parentheses. All right, so now we have this. What we have to do is talk about what's going to happen when this dissociates when you put it into water. How is it going to fall apart? Well, this is where it breaks down into its ions, which are lead 2 plus, and then we have the 2 acetate anions. So we'd write C2H3, 2 minus, and there's 2 of them. Now, the problem, what is being given here is we have a couple important pieces of information. One, we have that we started with 0.400 moles of lead, and then it's asking us what is the volume of that 0.150 molarity or molar lead to acetate. So what exactly should we start with? What is the term by itself? Well, if you remember, molarity is a conversion term. Moles is something that's by itself. So probably the thing that's going to make the most sense is starting with moles, because it's a number that you can leave in the numeral and we can't easily flip it. So let's start with that. All right, so if I have moles of lead 2 plus ion, what we want to do is figure out what our volume is. So how can we convert it to molarity, which is your other term here, right? Molarity is moles over liters. So in order to bridge that gap, we can use our dissociation equation that we wrote here. And that's that 1 mole of lead 2 plus is equivalent to 1 mole of PbC2H3O2. Okay, it's a very big formula. All right, so now when we do that, well, how can we bridge the gap to liters? So that gives us moles to moles. Now we can use our molarity for the last little bit to get the liters, which, as we kind of pointed out in the problem, is that we have 0.150 molar or moles, and that's equivalent to every 1 liter. So what we'll do here is do 0.4 divided by 0.150, and we will get our final number. And we'll have about 0.267 liters, or about 267 milliliters of our solution here that's going to have this much lead inside of it, okay? So being that the problem did not specify which units, we would leave it in the SI unit, but if you had to convert it to milliliters, you could do that too. Let's look at our next problem, which is a continuation of what we have here. So with this following problem, we're going to be doing a limiting reactant or a limiting reagent problem, focusing around precipitation. So when you have two solutions mixed together, it's a very realistic possibility that you will have a solid or maybe even a gas that results as one of the products, meaning you have to combine it with the different parts of stoichiometry, whether it's mass-to-mass stoichiometry or gas law stoichiometry. So with this one is when the volume of 1.50 molar lead acetate, and meaning that what says this volume is referring to the one that we solved in the previous problem, reacts with 125 milliliters of 3.40 molar NaCl. How many grams of solid lead to chloride are made from the reaction? And I have the reaction shown here that is balanced to save us a little bit of time in this video. So when we have this, what are we going to start with? Well, the first thing is you want to stay organized with all your pieces of information. So the very first thing is that being that it is a limiting reagent problem, how do we know that it is? Well, generally the telltale sign is when you are given both the volume and molarity for each solution. So we were given a volume of 0.267 liters with 1.50 molar. And then on the other hand, we were given 125 milliliters of NaCl with 3.40 molar NaCl. So we were given both starting volumes and concentrations. You need both in order to be able to solve for moles. You need to be able to cancel out the liters component. So with that, what we are going to do first is, well, we need to solve for the number of moles of each individual ingredient because we want to know how much lead chloride was made in the problem. So we're going to convert both of these guys, essentially starting with their volume for both, convert them to moles for each of them. So go from liters to moles. Then what we will do is go to moles of the product. We're going to compare both of them. Whichever one makes less is our limiting reactant. So the first one that we'll start with is we will do it with our lead acetate. So what did we have to begin with? We had 0.267 liters, and we're going to cancel that out with the molarity, which was 1 liter is equivalent to 1.50 molar lead acetate. So let's kind of copy and paste that down. Okay, so we're going to just put that above here. So that's of lead acetate. All right, now what we will then do is we're going to convert that to moles of lead chloride. So by reading our chemical equation, we see that for every 1 mole of lead acetate, we also have 1 mole of lead chloride. And that's using the coefficients to help guide where that conversion came from. So when we look at our chemical equation, we see we have a 1-to-1 ratio. Now, when I solve that, what I am going to end up getting is about 0.04005 moles of lead chloride made. Now, what that tells you is that if you use every single milliliter of lead acetate, and this is how much you're going to make if you use up everything, if it runs out. So this is your theoretical yield if you use everything. However, we don't know if that's going to be the answer. So we got to do the same thing for NaCl. So in this case, we have 125 milliliters of NaCl, and we're going to first convert that to liters. So we have 1,000 mLs is 1 liter. Then we are going to use the molarity to convert that. So 1 liter is 3.40 moles of NaCl. Then we'll use our chemical formula, which is 2 moles of NaCl is equivalent to 1 mole of lead chloride. All right, so when we do the math for this one, what we will do is 125 divided by 1,000 times 3.40 divided by 2. And what you will get is 0.02125 moles of lead chloride. So now what we're going to do is we're going to compare the top value with the bottom one. Which one is a smaller number? That's going to be your answer because that's going to denote your limiting reagent. So what you can see here is the bottom one. So using NaCl ran out first and made a lot smaller of an amount. Notice how it's about approximately half the size. So this is going to be your limiting reagent. Now, are we done? I wish. So what we have to do is now convert this to grams. So, which is our final step. So we're going to use our 0.02125 moles of lead chloride. And then how do we convert that to mass? Is we're going to use the molar mass. So we need to use our periodic table to find the molar mass of lead chloride. I already did that for us, which is about 278.1 grams of lead chloride. And that's equivalent to every 1 mole of lead chloride. And once we do that, we'll multiply those two numbers together, and we will get about 5.91 grams of lead chloride as our answer. Okay, so that's how much precipitate or solid should form if both of these two chemicals mix together. Let's go take a look at our next example. 42 milliliters of 0.35 molar Ki solutions required to completely react with 50 milliliters of lead nitrate solution. What is the original concentration of lead nitrate? So whenever you see what is the concentration, this tends to sometimes confuse students because they're not sure what to look for. Now, it's what we're thinking? Well, concentration usually refers to molarity in chemistry. It can refer to percent concentrations as well as molality as well, but 9 times out of 10, it's referring to molarity unless it's specified otherwise. So the first thing we need to do is define our chemical equation and balance it. So what we have is Ki is going to react with lead nitrate, meaning that we'll have inside reacting with outside. So the first thing we're going to do is, being that we have lead to nitrate, is that we will take lead as our inside and we're going to bond it with I, which there are 2 iodines to help balance that, right? So we drop both those charges. Now, potassium, which is a +1 charge, is going to bond with nitrate, which is a -1 charge. So we have KNO3. Now, when we are balancing these, one of the easiest tricks is balance the polyatomics first. Meaning that if you see on the left-hand side, I have 2 nitrates, and on the right-hand side right here, I have 1 nitrate. So what I'm going to do is I'm going to put a 2 in front of KNO3. The nitrates are now balanced. I'm now going to take a look at the potassiums. I'll put a 2 over here, and now the entire problem is now balanced as a result. All we had to do is kind of zigzag back and forth. Make it easy to balance. Start with the polyatomics. Now, what we now have to do is write down whatever our important piece of information, and we want to try to include all mole ratios. So what I'm going to do is I'm going to move this little step down, and we're going to write all this down below our chemical reaction to help us stay organized. The first thing is that we had 42 milliliters of Ki with a concentration of 0.35 molar. Now, the other part that we were given is that we have 50 milliliters of lead nitrate, but we don't know what the concentration is, which is the missing part that we have. So, and that's what we're trying to figure out. So where exactly should we start this problem? Well, we want to let the units guide our process. Now, but there's a little trick to knowing this, is that the side you always start with is the one that contains both the volume and the molarity. It has to have both of those pieces because you need to convert to moles. And the only way you can do that is if you have molarity and you have the volume to cancel out the liters component of molarity. So we're going to start right here on the Ki side when we are doing these different conversions. And we always want to start with the term by itself, which in this case is the volume, right? So we'll start with the 42 milliliters when we convert this problem. So we'll take 42 milliliters and we'll convert that to liters. So that way we can get to using our molarity, which is our next term. So if you remember, 1,000 mLs is equivalent to 1 liter. And then what we're then going to do is convert that to moles using molarity, which, as you can remember, if you see in the top left of your screen, is that 1 liter is equivalent to 0.35 moles of our Ki solution. So we want to label what the solution is so we don't get mixed up. Now what we're going to use is the chemical equation here. And what we can see is that 2 moles of Ki is equivalent to 1 mole of lead nitrate. That is from your chemical formula. So we have 2 moles of Ki, and that's equivalent to 1 mole of lead nitrate. All right, so that gets us to moles, right? Our goal is always the mole. Now, what we'll do is we're going to calculate how many moles there are. And then in order to get this into molarity, so if you remember, molarity is moles over liters. This first portion will give us how many moles there are. The liter component is, if you remember, we started with 50 milliliters, which is how much the problem told us we have. We'll divide that we'll convert that to liters and then divide this number by that. So when we do the math here, what we are going to be getting, so we'll take 42 times 0.35, divide it by 1,000, divided by 2, and we will get 0.00735 moles of lead nitrate. And what we are going to then do is we're going to take that number and divide it by 50 milliliters converted to liters. So it's going to be 0.0735 divided by 0.05 liters. Okay, so that 50 mLs gets converted. Now, once we solve that, what we'll get for our final answer is 0.147 liters as our final answer. And we have 3 sig figs because we started with 3 sig figs. And that's how you would solve, essentially going through your entire process to how to figure out how much volume there is. So what did this video show you? We went through how to find volume, we went to find mass, how to find molarity, and the biggest thing was how to use molarity as a conversion term using balanced chemical equations and how to use mole maps to help guide your thinking, right? So this whole process is a long one, but it's something that the more you practice it, the easier it's going to get. And you can see stoichiometry is all about how can you really make those units cancel, right, as you go through them. So if this video helped you, I appreciate it. And if it didn't if it made it was a little confusing, please ask questions and let me know if you need help. I'm always here for you. Please either send me a message, email me, or reach out to me. Or if you want to, you can even comment in the videos below and let me know what you thought, or if you have a question in particular, or if you can find an error, that's always okay too. And if this is your first time here, please like this video and subscribe to the channel for more introductory chemistry content to help you guys pass chemistry. All right, thank you so much, and I hope to see you all next time. Bye now.